Hi, today we're going to talk about glass fractures. This is our fifth property of glass that we can use to compare different glass samples. And because this has a lot of information to it, we kind of separate it from the other properties of glass like color and thickness and density and refractive index. So let's take a look at glass fractures. The reasons that we analyze glass, here's a couple of reasons. So the uses of glass, it can link a suspect to a crime scene. A lot of times glass has blood and or fingerprints on it that we can use to pull information about our suspects. And then how the glass breaks tells a story of the crime. Was the window broken from the inside or outside of the house? Did this shot or this shot come first in a shooting? So on and so forth. So all of these are ways that we can use glass to help us solve crimes. So we're going to start with the basics. There's three types of fractures. We're going to focus on the two most common ones first. Radial fractures are lines that radiate out from the origin of impact. They begin on the opposite side of the force, and they're the first fracture to show up. So radial fractures, if this is are lines that radiate outward from the origin of impact. They're on the opposite side of the force. So if the force came from the inside of the house, the radial fractures would show up on the outside, and we'll show you why in just a second. And they're the first fractures to appear in an actual break situation. Concentric fractures are the second type that you can have. And concentric fractures are lines that are found that are circular around the point of impact. They're on the same side as the force, and they're the second fracture to show up. So concentric fractures look like this. And I'll show you an example of both of those in just a second. So radial fractures radiate outwards, opposite side of the force, first fracture to show up. Concentric fractures are circular lines around the point of impact on the same side of the force, and the second fracture to show up. So let me show you an example here. You can see here, let's see if we can do radial fractures. This right here is a radial fracture. This is a radial fracture. This is a radial fracture. And this picture is in your notes, and I highly recommend you highlight the radial fractures one color and label them. Okay, those are all the radial fractures. And then you can see here's the concentric fractures. They're the circular ones that go around the point of impact. So here's your point of impact, and those are the concentric fractures that go around it. So my recommendation is for you to pause the video and to highlight the radial fractures in one color and then label them radial, and then highlight the concentric fractures in a different color and then label them concentric, so that you know the difference between the two. And again, here's another example. You can see here, these are all the radial fractures, the ones that are going outward. Okay, and there's a whole bunch. And then here's the concentric. You've got a concentric here, you've got a concentric here, here, here. They're the circular ones. Okay. Again, here's just another example. Your concentrics are here. There's a concentric here and here. And then you've got a bunch of radial fractures as well that are radiating outward. Okay, so radials go outward and concentrics are circular. The next thing that we're going to talk about is the direction of force. A projectile hole is inevitably wider at the exit side. You're going to want to jot that down. The exit side of a projectile hole, so if you shoot a piece of glass with a bullet, the side that the bullet exits the glass on is going to be wider, and here's kind of why. We're going to take a look at that. You can pause the video if you need to write that. But here's how it works. Okay, so here's your original piece of glass here. Okay, the bullet comes in right here, all right? It hits the glass and it causes tension on the glass. So the glass is like straight up and down, and it causes the glass to bend just a little bit. Well, eventually it bends to the point that it can't anymore and it breaks. And this first break right here, those are the radial fractures. And notice the break is on the opposite side of the force. Well then, because it broke here, it creates more tension on the glass a little bit higher or a little bit further away from the original break. Those second breaks that happen, those create the concentric fractures. So that's where you get your circular patterns out here on the edges. And then you can see, because the glass broke on the opposite side, the shards come off the opposite side, which means right over here in this area is going to be the exit side, and it's going to be larger than the entry side. It's kind of like the same thing if somebody gets, like a person gets hit with a bullet. The entry wound is usually very small, just the size of the bullet, and then it blows out the back of the body, and the exit wound is much larger. The same theory works with glass. Okay, so you can, on the picture, you can label where the radial fracture and the concentric fractures happen, and then I would recommend that you circle this area here and you put exit side larger so that you know. The third fracture that happens in glass, so far we have radial, we have concentric. The third fracture is called conchoidal fractures. And conchoidal fractures show up on the edge of the glass. So if you were to take a piece of glass and you were to look at the thickness part of it, the edge, that's what we're looking at conchoidal fractures. And conchoidal fractures follow what we call the 3R rule. And the 3R rule says that radial cracks, so you have to be looking at a radial crack, you can't be looking at a concentric one. Radial cracks form a right angle on the reverse side of the force, the opposite side of the force. So if you're looking down here, you can see that there's these lines and they're coming down like this, and they're hitting here at the bottom. Okay, like this. Well, as they come down like that, they're forming a right angle right here. Okay, like a 90-degree angle right here. So they're kind of parallel up here, and then they come down and they form a right angle down here at the bottom. Because the right angle is down here, the force came on the reverse side. So the force hit the glass up here to form the right angle down here. So radial cracks form a right angle on the reverse side of the force. Okay, so if we were to draw, let's see if we can add a couple more in here to give you a little bit better understanding of this really quick. So if I were to draw some fractures, and they looked like, sorry, that wasn't a very good one. It's hard to write with these pens. I'm going to try that one more time because I don't want to get you confused. So if these were my conchoidal fractures, you can see that they're coming in and they're forming right angles down here at the very bottom. They're forming right angles down here at the very bottom. Okay, so there's my right angle, there's my right angle, there's my right angle. So that means the force hit on the opposite side. So the force came from the top, not the bottom. If I were to draw another one over here, let me see if I can give you an opposite example. And I were to draw, and I drew them this way this time. And I had a whole bunch of conchoidal fractures, and they were going upwards like this. And here's where my right angle is hitting. Right here. Now the right angle's hitting up here, which means my force came from down here. So now my force came from the bottom instead of the top. Okay, so radial cracks form right angles on the reverse side of the force. Okay, so that's the third fracture. So you've got radial, concentric, and then conchoidal fractures. And I'll try to, in class, I'll try to show you what one looks like on the side of the glass so you can get a feel for that. Okay, the last big point that we want to make for fracture patterns in glass is successive points of impact. Successive points of impact, the rule is a fracture always terminates at an existing line of fracture. So you're going to want to write this down. A fracture always terminates or stops at an already existing line. And that's how you can tell which one of these came first. So this is, if this was shot A and this was shot B over here. Oh my goodness, sorry. Let me try that again. Let's do it a different way here. So if this was shot A and this was shot B, okay, right here. Okay, we can tell that shot A came first before shot B, and here's how we can tell. Right here is a radial fracture that's going out. It goes, and then B happens, and its radial fracture goes, and it stops right there, which means A's was there before B was shot. So A was the first shot, B was the second shot. There's another one down here. You can see that this was a radial fracture from A and that it went out here, and you can see that B's radial fracture went and stopped. So there's 2 points, one's right here and one's right here, that both show that this was the first shot and this was the second shot over here. Because a fracture always terminates where there's already an existing line of fracture there. So it goes, and when it hits one that's already there, it stops going. Okay, so you can tell that A came before B. Here's another example. So if this is A and down here is B, I guess you can't really. This is A and this is B. You can take a look and you can see that A came before B right here. This is the big line right here. This one goes, B stops right at it. Here's A's, goes like this. B stops right at it. So you can tell that this was shot 1 and this was shot 2. Okay? So an already existing line that's there will stop any that are coming towards it. And here's another example. So if this is A and this is B over here, okay, and we're trying to see, did A come first or B come first? In this case, I think B came first, and my thought process is right here. Okay, so there's B's radial fracture, and A comes down and stops right at it. It's kind of hard to see over here too, but I think this is B, and then A comes and hits at it right there as well. Okay, this one gets a little bit messier because there's some big chunks out of it, but it looks like I would say that this one came before this one. So B came before A. So the successive rule is that a radial fracture stops at an already existing fracture. Okay, all right. That's it. Those are the big rules for the different types of fractures. We'll do a lot of lab practice this week to get more comfortable with understanding the different fracture patterns and how glass breaks and different things like that.